Okay, so Norton is what's on the menu right now. So we're going to look at Norton Theorem. So let's look at an example again, just like we did with Thevenin. Let's suppose we have some sort of a source voltage and a current voltage. So similar example to what we did in the previous video. Some sort of an internal resistance here as well for the system, and a load. And here's our RL. References A and B here. Okay, we could, if you want, make this your ground reference if you want to. This would be R2, R1, E, and I. Okay, unlike Thevenin, if you remember Thevenin, we wanted this, either way, it will be a system with two poles, A and B, like this, okay? And we will connect RL here. So if this was a Thevenin circuit, then you would end up with an equivalent circuit inside of it that looked like this. So this would have been the system, okay? This would have been A and B. This would have been your load, and this would have been RTH or R Thevenin, and this would have been ETH for E Thevenin. In our case, so this was Thevenin. In our case, we're looking at Norton. So the systems are going to be the same. Either you use Norton or Thevenin, the results will be the same. Except for Norton, what we want is a current source, an internal resistance, let's call it RS for now, and your point A and B will be right here. And again, your load will be right here. And maybe we're interested in the I load here, just like we were interested in I load for the Thevenin equivalent. So again, our system will end up being this. So we're going to go from all of this right here, looking into something like that. Okay, so some textbooks like to call the RS that we have here RN, as in R Norton. Let's call that. And this here, we're going to call it IN, as in I Norton. Total. Okay? All right, so how do we go about it? It's extremely similar to Thevenin. First, we're going to need to figure out Rn. So we'll start with that. So we're going to look for Rn. What is the R equivalent seen as a Norton equivalent circuit, right? So to do that, the principle is the same you did in Thevenin. So you're going to short your voltage source and open your current sources, which if we take this circuit right here and do just that, we will have a short for E. R1 will be here. We will have an open for the current source. And we would have R2 right here. And again, we are interested in R, or the internal resistance, seen in this manner. So we're looking at Rn from this point of view, from A and B. Now, obviously, that will connect to the load later on. So right now, this is what we're looking at. So what do we see? We see two resistors in parallel, right? So Rn, in our case, will be R1 in parallel with R2, which is really R1 times R2 over R1 plus R2, and that would be Rn. Good. So we can plug that figure right here for the equivalent circuit. So now we want this one, okay? While this one, we're going to do it in several steps, okay? So just like we did with Thevenin, we're going to have to put back our sources one at a time, okay? So, and we want to figure out what is the current that any of these systems will generate. Here's the major difference, however. So I need you to pay attention to this. Whatever we do, we're going to shorten out A and B. So let me repeat. We're going to be shorting A and B. And we want to measure the current as it goes through A and B. So, okay. All right. So first, we're going to put our voltage source right here. Here is R1. This is E. We're going to leave the current source open. We're going to put R2 back here. But for Norton, this is the particular solution. So we're going to put a short right here. Okay. So, what would happen? Let's think about what happens here. Okay, so if we have a short, that means the only current going through the circuit, obviously it's going to bypass R2, so all of your current is going to go through the short. So R2 is not going to get any current. That same current obviously is coming from somewhere, so it's going to traverse R1. Aha. So let's call this one I Norton 1 right here. And this will be the same here, I Norton 1, generated by this power supply. So what do we technically have? We have a power supply with a resistor and a short. So that is still, R1 is still supplied by voltage through E. So the current IN1 will be equal to E divided by R1. Excellent. So now let's go back to shorting E and opening I. So see, you're going to short E. So if this was our reference, just so we know. So we could put R1 this way. So that would be R1. I like to draw it this way. And let's put our current source this time. Okay, as you can see, the reference will still be here. And let's put R2 right here. And let's measure A and B. Okay. So what's going on at this stage? We've shorted R2. Do you agree? We also shorted R1. So let's think about exactly what's going on here. Can I switch? So this point here is the same here. This point here is the same here. We could do this. Just so I can illustrate this even better. This is R1. This is R2. And that's your short. This short here is shorting these two resistors. So the only current you really have through the short is whatever I was. Whatever I that you had here. So IN2 is going to be equal to I at this stage. Okay. But now, what is this IN? Now, for this IN, you're going to now, this is what makes it different than Thevenin, is you're going to put it in the circuit, and you're going to figure out what IL is, right? So let's go ahead and do that. So what would be IN? Right here. And remember, you have this partial current here, and you have this partial current here. Okay? Now remember, that is not I load yet. A lot of people jump to conclusions and assume these two are the I load. They're not. Okay? So I load here, we still don't know that. Now that I'm considering the load back into this circuit. Now remember, this is Rn. We already figured that out. Okay. All right, so that's that value right there. This one here will be the sum of these two right here. So this In will be E over R1 plus I. Okay, so what would be IL? Well, for IL, we could do current divider rule. So if you think about IL, it's going to be equal to IN times Rn divided by Rn plus R load. Now we could replace In here with what we have here and see what that gives us. Okay, so we're going to substitute In by this value here. Not that it will make a major difference. So let's see what IL might look like here if we did that. And that would be E over R1 plus I, all of this times Rn divided by Rn plus RL. If you had to simplify this, that would be ERN, or you could factor out the, you can keep, well, we could do that. ERN over R1. We could multiply and divide R1 and R1 here times I, the whole thing divided by Rn plus RL, and that would yield ERN. We could factor the, let me see here, we could factor the Rn and that would be E plus R1I, everything divided by R1 times Rn plus RL. Okay, now as you're processing this, you probably would stop here once you have all your results. Okay, now this is just in case you wanted to explore further what will be a final formula for IL. I don't think for most cases you will go this deep. You most likely will stop right here. Since you'll be plugging in values that you already have, right here, Rn and In, that you've deduced previously, and should give you the IL here. Okay, this here just in case you really want to go into exploring how this relationship between IL and the resistors might be.